Okay, so I think, yes, so, okay. Right, so let's start then. So basically for the end, for the next few lectures at the end of the course, the idea is to compute the cohomology of some manifolds. Basically, we need two main ingredients. One of them was the subject that we covered last time, and that is the major Viettori sequence. And the other important ingredient that we will need are some concepts of topology or algebraic topology. So that's why, so we will cover homotopy type of manifolds or topological spaces. I don't know if you have seen this in a topology class or a algebraic topology class. So this is what we will do now. So as I mentioned, that's the goal, to compute the cohomology. Now, have you seen a homotopy between maps? What is the definition of two maps being homotopic in terms of topological spaces? Is that a yes or a no?
Yeah, I think so. Like we have a mapping from I don't know, let's say 0,1 times whatever space we are in,
Right, okay.
and to the same space such that.
Right, so there's some idea. Nonetheless, we are going to go into that. Okay. So first, so we have this. I mean, if two manifolds are diffeomorphic, there is a smooth map between them, and it is a bijection, and the inverse is also smooth. And when we know that two manifolds are diffeomorphic, we have seen that this map is a linear isomorphism. Actually, we saw a little bit more. We saw that it is an algebra isomorphism, but let's just do it degree by degree. So because we are interested in computing the cohomology, if I have a manifold and I know that it is diffeomorphic to the other one, then I know the cohomology of the other map. And in fact, I know how they are related via this map. Okay, but now the concept of two manifolds being diffeomorphic is very strong. It is very strong to restrict only to diffeomorphic manifolds. There is a weaker notion between manifolds that guarantees the same conclusion. So the whole idea is not to remain on diffeomorphic manifold, but a weaker concept that we will see, but the conclusion will be the same. Okay. And that's where homotopy enters. So I'm going to to explain roughly the idea behind homotopy. And I'm going to do it in a special case that you have already studied in complex analysis or calculus 4, complex calculus. So I'm going to look at this set of maps between the circle and R2 minus the origin. So for the time being, I will consider only continuous functions, although for this class, we will need them to be smooth, because this and this are manifolds, so it makes sense. But for the time being, let's only consider continuous functions. Okay, so we are here on the space of continuous function between two topological spaces. Okay, so this is a very natural thing to do. I have two topological spaces, and now I look at the map of functions between them. Now, because this is a topological space and this is a topological space, this one here is also a topological space. Okay, this is something that you see on a topology course. So, and the reason that I want to emphasize on having a topology here is because I would like to consider what are the connected components of that space. Okay, now of course we could be interested in more information about that space, more topological information. But for the time being, only what are the connected components? Is it path connected or is not path connected? Okay, and in order to talk about something being path connected, the topology is relevant. So here I put this, but remember that the C infinity topology, we require this to be C infinity maps. So, but with the C0 topology or the compact open topology, that's enough. Right. So let's try to understand in this space what it means for 2 points to be connected by a continuous trajectory. So consider two maps, and let's assume that they are in the same path connected component. That means that there is a smooth path between those two maps. And this is what Salvador mentioned, the 0-1 aspect. So the whole idea is this is the domain, codomain of a set of functions. And I want to move between one function and the other in a 0-1 time lap. So at time 0, I'm at F0, and at time 1, I'm in F1. So now I have a one-dimensional, so to speak, dimensional because of this, a one-dimensional collection of smooth maps from the circle to the complex plane minus the origin. The initial point is F0, the end point is F1, and well, I wrote here smooth, but let's do it correctly here. continuous. Okay. Because I'm talking about continuous functions. If I talk about the space of smooth functions, I will require the function h to be smooth. But you see, it happens, there is something very interesting going on. And this is zero, 1 is a very nice space. Instead of thinking of a curve on this space, here we have the compact open topology or some topology on the set of functions. R has to be a continuous function. R0 is F0, R1 is F1. So instead of having that, we have the other function. Something that it is more appealing, which is this function. Okay, but the guys, I know that this is shocking and very interesting, but come on, what he says. Right, so this, which is like the expression for a path, unwinds into something like this. And this is more appealing because I don't have to deal with this more complex space, and I have something more familiar. This and this. Okay? So that's the big advantage here. And so basically making this smooth in the compact open topology of the space of maps is equivalent to having this smooth. Or continuous, sorry, continuous. Okay, so that's the whole idea. Something more complex, we are looking at it in a more basic way. And so, coming back to our original problem, the path connected components of the space of functions. So, we still don't know if it's connected or not, or how many connected components do we have. But now we have the notion of what it means for two functions to be in the same path connected component. And now, basically, everything that I have said, it doesn't matter for if my domain is S1 or any other topological space. And if my codomain is the complex numbers minus the origin, or any other topological space, it would work. But now I would like to use that in our advantage to understand the connected components. So remember that we have the winding number, and that's why I'm using now the complex plane. If I have a closed curve on the complex plane, that curve is going to be the image of the function, the closed curve, Then, oops, this is, what is the winding number? I'm missing something here. This is incorrect.
It comes center.
Sorry, come again? Salvador, please.
We need some point of reference. Right?
I'm sorry?
So we need some point of reference.
Oh, okay. Yes, but you see, my mistake is that I'm integrating a constant function. So this is wrong.
Yeah, that should be used 1C.
Yes, exactly. That's my mistake. Sorry for that. Yeah, that's wrong. C, or I can put C minus 0, right? That's why I decided to omit the 0. And now here I need this. Okay, now that is an integer. If I make the path integral along any curve that doesn't go through the origin, and that's why f goes from S1 to the complex numbers minus the origin, that is a number, an integer, and that's the winding number of the curve. Okay? Right. So this is something that you study. But not only that, I mean, you actually really got your hands into this. And you know that to compute the winding number of some curve, here I just wrote a simple closed curve. It doesn't intersect, but that can happen. And remember that the orientation is important, right? For instance, for that example, what is the winding number of that? Of that curve, what is the winding number?
Just one.
One, usually counterclockwise is positive, okay? And again, in the same curves, what you were doing, you will say, well, this simple closed curve is homotopic to a small v, or maybe the unitary circle or whatever. So they are homotopic. That's what you studied when you were looking at the winding number, right? And now I can draw a different curve. Again, I'm going to stick to simple closed curves. Well, sorry, it's no longer like this. So for that, the winding number is 3. And also you can shrink it to a small disk, but now you will go around 3 times along that, okay? And this is a result that you study there in terms of curves in the plane. If they are homotopic, they have the same winding number, and the other way around. If they have the same winding number, they are homotopic, right? And the important aspect of considering this is that being homotopic is an equivalence relation. So basically you would take any closed curve and then it will be homotopic to a small or the unit circle. going around that many times. And that's how you know that they are homotopy and have the same winding number. Okay, so this result, this if and only if, answers our initial question. The number of connected components of the space of functions. So basically, we have a countable number of components, path connected components for this space. So this is for smooth maps, but if you do the same and take a smaller class of, I'm sorry, this is for continuous. If you take a smaller class of smooth, the same will hold. There's no distinction whatsoever, right? So in this particular example, homotopy, as always, in the general case, homotopy between maps means they are in the same path connected component. And in this particular example, your knowledge of the winding number allows you to understand all of that very well, when they are homotopic and when they are not. So, any questions up to this point? Now, I'm going to change this, and I will change it exactly in the same way that you did in complex analysis. Instead of taking the circle, the complex numbers minus the origin, I'm going to take the circle, the unit circle. Okay? And now, so remember that I have been talking about continuous function. Now I will restrict to smooth functions. And the reason that I want to do smooth functions is the following. Now here, there's no problem. You know that that is a smooth manifold, and this is also a smooth manifold. But you will see why I will prefer to have S1 and S1. If that map is smooth, we have the induced map in cohomology, and basically it is a linear endomorphism. I'm going from a vector space to itself. And not only that, last class we computed the cohomology of the circle. So what is the cohomology of the circle?
R.
In which degree? So I have K 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm waiting for one of you to stop me.
It was at 0 and
For K equals 0 is, what it says?
R.
R. That's correct. For K equals 0 is R. For K equals 1?
It was R times R. And
No, for K equals 1 is not R times R. It's not R2. Salvador?
Yeah, I can't remember either.
Come on, guys, you need to study for this. You need to take it seriously. So for K equals 0 and 1, it is R. And for the other case, it is 0. Right? So then F star is a linear map from the reals to the reals. Okay? Now, remember that basically this is like a GRE question or a head question. What are the set of linear maps from the reals to the reals? The real has a vector space. So any linear map is like what? So a linear map from the reals to the reals. Come on. So you have a vector space of dimension 1. The linear maps. If you choose a basis, it is a matrix. A 1 by 1 matrix. Right? One that you put a basis, then any linear map is, in general, right? I mean, the set of n by n matrices corresponds to the linear maps of a vector space once that you choose a basis. So if this is R in R, let's assume that my generator is the vector 1, then any linear map is a scalar times the vector. That is the set of linear maps from R to R. Okay? So coming back to our problem, so I know this is R, this is R. I want to know what is this function. And it happens that, so all that I need to know is what is A, right? I want to know what is the value of the real number A. And in this case, it happens that when k equals to 1, this is just multiplication by the winding number of f. So that's in degree 1, this map is this. Okay. Any questions?
Why the winding number?
Yeah, right. Yes, so That's why I said extra. Right now, we are not going to prove this. Okay. Now, let's see. Maybe let's forget about cohomology and so F is a map from the circle to the circle. And we have the winding number, right? The winding number is telling me how many times am I going to cover the target and also in which direction. Now, instead of looking at homology, did you look at the fundamental group? Or not? In algebraic topology, did you study the fundamental group of or topological space?
We did see it, but I can't recall any of the details.
Okay, but so it has to do with some loop, some closed curve that doesn't wind. Let's understand this function. Let's take a generator here. A generator is a loop that goes only once along the circle. Either direction, it could be the positive generator or the negative generator. So G will go only one. Okay, now the other thing to note, different. This map is, sorry, here the fundamental group of the circle is the integers. Same question as before. You have a group, the integers. What is the set of automorphisms of the integers? It depends only on the generator.
What?
The group automorphisms of this. In general, you have a group, and the question is, what is the set of all group morphism from the group to itself? So it is the same question as before. but the other question was in the setting of linear algebra between vector spaces, but now in group theory. The good thing is that the integers are cyclic. It's a cyclic group. So you have a generator. And in order to determine the set of all morphisms from a cyclic group, you only need to consider where do you map the generator. So this is C. Basically, any map alpha of some group element is going to be A times. So it's G times G times G times G, depending on the notation. So I'm using additive notation here. If we use the product or multiplicative notation, like this, right? Let me put it like this. A times. So any morphism from the integers to the integers is determined by one number, one integer. So let's come back to this. I have a function from the circle to the circle. For what we have seen before, is basically going around the circle, sometimes in one direction or the other. And I want to understand what is this? This group map, this group homomorphism. So I take a generator here. That is, I go along the circle only once. Right? So no moving on now. Okay, so I want to understand this map. By definition, this map is G composed with F. What can you say about this map? F goes K times and G only once. What can you say about that map? Moises, you have the shadow in your face. I cannot see you. Great. So in terms just of the geometry, what can you say about that map? It is a map from the circle to the circle. How many times am I going around?
Three
Many
times.
as F.
Right. Exactly. So this is homotopic. 2. I put an equal here and doing G and then go around, as many has the winding number. Okay, so this argument corresponds to this one here, but in fundamental groups. This is in cohomology. So that's without going into the cohomology, which we are learning right now. That's an idea of why you have this map, and this is like trying to answer Salvador's question. So this is the answer, at least for fundamental groups, not in cohomology. Okay, Salvador?
Yeah, okay.
Right. Nice. And I mean, it is very interesting actually to go into this. I don't know if we will have time for that. Okay, but let's see. Okay, so any questions?
Nope.
Well, so remember, so far, all of this was just to recall, at least in some specific case, the homotopy concept. So let's now go to the actual definition. So this is the same definition as the one that you saw in topology. So two functions are said to be homotopic in a naive way if they are in the same path-connected component. If there is a path from one to the other. That's basically what I'm writing down here. Okay? But now, because now we are in the smooth setting, M and N are smooth manifolds, F and G are smooth manifolds, H has to be a smooth manifold. Okay? Now, so everything is the same. At time 0, I'm at one map, and at time 1, I get the other map. Nothing new there. But there is a slight thing that I really want to discuss. If you see the book starts with the definition of manifolds, and then there is a chapter regarding manifolds with boundary. We didn't cover manifolds with boundary. And that's the issue here. I'm saying that this is a smooth function, but this is not a manifold. Okay? The target is a manifold, but not n cross 0, 1. So if you really want to go away and look at manifolds only, then we can replace the closed interval by an open interval, and then everything works well. Okay? We can replace 0, 1 by this interval, and again, H at 0 has to be F, and H at 1 has to be G, and that's it. Okay? Good. So that's what two functions mean to be homotopic. And basically, by looking at everything that happens on one connected component, it could be huge, the path connected component. But the important fact is any of the maps there is there, in terms of the induced map in cohomology, they are the same. So I don't get anything new whatsoever. If I have two homotopic maps, the induced map in cohomology are equal. So this is something very useful. So the functions that lie on the same path connected component are going to induce the same maps in cohomology. Oh, sorry, and this is for every K. Okay. Now, remember that this is something that, this is how we started the class. Sorry. When M and N are diffeomorphic, we have that. Here, we will do some examples next, but M and N doesn't have to be diffeomorphic. You only require to have a homotopy map between them. Okay? So later we will see examples of this. And in fact, just so that you can note, if two manifolds are diffeomorphic, they must have the same dimension. We will see examples of this where the dimension of this is distinct than the dimension of N. They have distinct dimensions. But then again, we obtain this conclusion. Right. I'm not going to prove this proposition. We will prove something else. And let's see now this definition. So this is the concept that we were aiming at. Instead of just being very narrow on diffeomorphic manifolds, we want to have manifolds of the same homotopy type. So two smooth manifolds have the same homotopy type. If I can find two smooth functions such that the composition is not required to be the identity. It is required to be homotopic to the identity. Right? So for diffeomorphic manifolds, I need to have equality here and equality here. That's what it means to be diffeomorphic. To have the same homotopy type, it is weaker. I don't require to be equal, just to be homotopic. These two maps. Okay? I don't know what happened here. Okay. So this is the concept that I really, really want, and this is what we're going to do examples. And the reason that this is useful is for this. Okay? So diffeomorphic is very rigid for the purpose that we want. So we have something more weaker, that is homotopy type. And here it is. If two manifolds have the same homotopy type, I have the same cohomology. That's the whole idea of this. Okay? So we will prove this proposition using this. Homotopic maps induce the same map in cohomology. Okay, so if these two manifolds have the same homotopy type, by definition, there exist two smooth maps such that after doing the composition, I don't get equality with the identity, but I have that they are homotopic. So this is a map that goes from n to n. It's not the identity, but it lies in the same connected component as the identity. And the same here. Now let's use the previous result. Homotopy maps induce the same map in cohomology. Then we know that the identity map induces the identity map in cohomology. And now homotopy goes to equality in cohomology. All right, and now I have a star here, the induced map in cohomology. And when I put this inside, what happens is that the order is reversed. That means that this map in cohomology composed with this one, I get the identity. And also the other way around. The composition of the other way, I get the identity in cohomology. So this map and this map are linear isomorphisms. Okay? So this space is isomorphic to this other vector space. Okay, so remember we have what it means for two functions to be homotopic. Using that, we define what it means for two manifolds to have the same homotopy type. And that is useful because manifolds that have the same homotopy type have the same de Rham cohomology. Okay, so now we are going to see examples of everything that we have discussed. Are there any questions before we proceed? Okay, so let's see this example. Now, I'm not going to use the winding number anymore, so I put R2 instead of C. And the first thing that you have to notice is that this is a smooth manifold of dimension 2, and this is a smooth manifold of dimension 1. So the dimension is not a restriction for something to be for two spaces to have the same homotopy type. So this is the interesting thing. Once that we understand this, remember that we know the cohomology of this, and once that we prove that they have the same homotopy type, we will know the cohomology of this space. So that's why it is useful to have this new concept of spaces having the same homotopy type. We will create more and more and more manifolds for which we will know the de Rham cohomology. And again, that was like the goal for the next few lectures. Okay, so we will prove that they have the same homotopy type by using the definition. Right now, we don't have any other mechanism to compute or to say that two spaces have the same homotopy type. So we need to look at maps. I'm going to consider the inclusion map. The circle, the unit circle inside the puncture plane. So a point in the circle goes to the point in the circle. The other map is the map that you have used many, many times. We just normalize the vector. We'll make it a length 1 vector, right? And that's the reason that we remove the origin, basically. Okay, so I claim that these two maps will help me to conclude that the circle and the puncture plane have the same homotopy type. So I have to compose both maps and show that they are homotopic to the identity. However, one composition is very trivial. This one is exactly the identity. The inclusion, and then the point is already of length 1. So I get P again. Right? So in this case, I got a stronger relation. The two functions are equal. I was hoping to be homotopic maps, but it happens to be equal. Now we have to, again, do the composition, but the other way around. Right? So I take any vector on the puncture plane. I will make it length 1, and then the inclusion will leave it the same. So here. So this is the map from the puncture plane to the puncture plane. And I want to show that that map is homotopic to the identity. Right? This is what we want to do. Once we prove this, we have shown that those two spaces have the same homotopy type. Let's just do a picture of what we're doing. I have a point, and then in the same way, it is mapped here. Okay, and the function that does that, I want to show that it is homotopic to the identity function on the puncture plane. So this is the function, right? So it goes from the puncture plane to the puncture plane. In some point, I need to get the identity, and on the other one, I need this function. And it's just basically, I'm just parameterizing this, right? That's all that I'm doing. Or if the point is here, so t equals to 0, this vanishes, and I have my function, this one here, at t equals to 0. And now at t equals to 1, I get the identity, right? So with this function, I'm just moving like this in time until I get here. If this is my point, I'm moving until I get here. So that function is a smooth function because the only problem happens when the vector is 0, but we are in the puncture plane, so there's no problem there. So this is a smooth function. And moreover, because it does what we expect at time equals 0 and 1, it is a homotopy between the two maps. And the circle and the puncture plane have the same homotopy type. Moises, any questions? Salvador?
Nope.
So what we are doing is consider the puncture plane. Everything that goes to infinity, we start to pushing it in until it reaches the unit circle. And what is inside, because we are missing the origin, everything that it is inside, we're pushing it out of the circle. That's the homotopy that we are describing there. Notice that if I put the origin, there's no way to make that function continuous. Forget about smoothness. There's no way of doing that in a continuous manner. Yeah, because where do you send the origin? If it goes here, well, but nearby points will be here, are everywhere nearby points. So it cannot be continuous. And that's important that the origin is removed from this. And I want to insist on this picture because at least we're going to use many manifolds of two-dimensional manifolds. And I'm not going to write the explicit H, the homotopy. Just by waving hand, show you can push out, push in, move around. You will be able to say that something is homotopic to something else. At least in dimension 2. In higher dimension, that's another story. So as a corollary, we have that we know the cohomology of the puncture plane. So can someone tell me what is the cohomology of the puncture plane?
R
In which degree?
for both 0 and 1.
0 and 1. And on the other ones is 0. Okay? So, and this is exactly what my intentions at the beginning. We can compute the cohomology of some spaces. We don't do any explicit calculation. We just use the concept that we learned about spaces having the same homotopy type. Okay, so now you have something more. So let's do more examples. Oh, yes. Actually, we need to go back here, and it is important for you to review all of this because the dimension is irrelevant. You can work out the same functions, but instead of having a point in R2, it will be in Rn. And you will be able to show that the function Rn has the same homotopy type, has the n-1 dimensional sphere. And in particular, they will have the same cohomology. So these two spaces have the same homotopy type, use the same function. From here to here, the inclusion of the n-1 sphere. And on the other direction, the normalization of the length of the vector. And that will give you the homotopy that you require between the two spaces. In particular, we will have that they have the same cohomology. Okay? Now, of course, we don't know this and we don't know that one. Eventually, we will compute the cohomology of the sphere. But so right now, it looks like an empty statement because we don't know each one of them, but eventually we will. Okay? So the proof of this proposition is the same as the one we did for the puncture plane and the circle. Now, Euclidean space. The Euclidean space has the same homotopy type, has the set that contains only one point. You can say the origin if you want. Okay? Usually it is denoted like this. So Rn has the same homotopy type, has the set that has one point. Now for this, let's just put something on the table. I don't know if we discussed this at the beginning, but a finite collection of points is a smooth manifold of dimension 0. Okay? So the set that consists in a single point is a smooth manifold, has dimension 0, and also the cohomology of that space, it is only R when k equals 0 because it is connected. And by dimension reasons, for k greater or equal than 1, the cohomology is 0 for a single point, right? Because we don't have any differential forms by dimension reasons. So that's why I have this here. It is 0. I'm not putting k equals to 0 because we already know that Rn is connected. So H0 of Rn is the reals. Okay. Is the proposition clear for you? So let's prove this. Again, we need to have two maps, do the composition and show that they are in the desired path connected component. So in some cases, we don't have many options. So what is a function that goes from the 0, 1 point to Euclidean space? So it's just sending a point to a point. I decided to go with the origin, but it could be any other point. So there's no options for F. And the same for G. I mean, G has to be a constant function. There's nothing more that I can do. Okay? Now, before I move on here, I forgot to mention, remember that this, we already proved this for n equals to 1. We use the fundamental theorem of calculus. We use the definition of the rank cohomology. We consider a 1 form and we show that it was exact. So for n equals to 1, this is something that we have already computed using the definition of the rank cohomology. Closed forms over exact forms. Okay, so I forgot to mention that. Great, so f and g, that are the functions. Again, I don't have many options. That's the only thing that we can do. So again, one of the composition, I get equality. I get something stronger than mean homotopic, the two maps. They are equal. So let's worry about the other one. The other function is a constant function. F composed with G. So any element in Euclidean space by this function is mapped to the constant. Okay, so now you have to think about this. I need an H that goes from this map to the constant map. Any ideas of what is the homotopy? At one point, you have the identity. At the other point, everything collapses to the origin.
T times the point.
T times what?
The vector.
And that needs to be the only thing to do, right? Scalar multiplication. That is smooth, right? And exactly at t equals 0, I have the constant function, and at t equals to 1, the identity function. And again, the way to think about this homotopy in geometric terms is at t equals 1, you have the identity, and as you move from t equals 1 to 0, everything starts to shrink. You collapse everything in a smooth manner to the origin. And that way you have that Rn and a single point have the same homotopy type. Good. Any questions on this part? Great. Now, let's do a couple of more examples, and they are related to what we saw in our previous class. So, this here. The cylinder has the same homotopy type as the circle. And do you know what I'm doing on the second item? So I'm looking at the unit sphere in Rn. So this is Sn minus 1. And I've taken this. Do you remember from last class? First, we look at the circle. And then we cover with something like this and something like this. And the intersection were two small intervals. And we used the measure sequence and computed that. And then we just discussed only in terms of open spaces, no longer the measure sequence for higher dimensional spheres. So I have, let's say S2 in R3, I have the sphere, and then I took a neighborhood of the equator. So that's why I have this. Note here, because this 0, this is an equator of the sphere. Okay? So basically, this was the intersection of U and V from last time. Northern hemisphere, southern hemisphere. And you get that. And the whole idea is, it's like a belt. A belt, we will shrink it to the equator. And that's exactly what we have in the case 1. But in the case 1, I put it more explicitly. It's just S1 cross A comma B. But you can think of that cylinder, maybe a little bit curved, along the equator, the belt. Okay, then, so let's start with this. We will only do one. So let's say that A is less than 0 and less than B. So I need functions here. In geometric terms, oh, sorry, it is the open cylinder, right? This is the cylinder. And the circle, I would like to think of the circle in here. Let's say at height 0, you have height A, 0, and V. So I need functions.
Maybe one is inclusion.
Hold on. Okay, now?
Maybe one can be the inclusion.
Oh, the inclusion. Hold on then. And G. So here P max to P, the inclusion at 0, so to speak. What about F? There's only one way. You need a point
P
in
as
the
well.
Pardon?
So P.
Yeah. Projection. So G composed with F, I have P, S. No, let me do I wanted to do the simple one first. This. Okay, so this is F applied to P, comma, 0, and that will give me P. That is the identity on this one. Okay, so this is cool. Now we need to compose the other way around. So this is G applied to P, and this is P, comma, 0. Right? So you want to show that this is what we have to show, the identity map on the cylinder is homotopic to this map. So tell me, what is this map?
ST,
S,
S times T.
so define is smooth, right? Now let's see. At 0, what is it? It's P0, and exactly this is that, right? Yes. And now at 1, exactly you get the identity on the cylinder. And that's it. All right? Let me just write it down. T times S. Because again, I mean, it is the same principle, T, and you are shrinking the interval A comma B. That's what you're doing only. The circle, you can neglect it. The whole idea is to take the interval A comma B to a point. So you are shrinking A comma B until it gets to 0. And that's exactly what we had before between the Euclidean space and being homotopic type to a point. It is the same map. That we had before. Okay, so this is correct. And with this, we end part 1. But Mark II is the same. Instead of having the cylinder, it is like a little bit curved because it lies on the sphere. And you want to shrink it all the way down to the equator. That's all you're doing. Okay? So that's exactly what you do. And again, so from part 1, you get new information because now you know the cohomology of the cylinder. Okay? Now, in part 2, we only know that they are of the same homotopic type, but we don't know them, right? We don't know any of the cohomology of the spaces involved, but just remember that this is an equator, so it's smaller. Here you have the sphere, and this is n-2. It's an equator of the sphere. So the whole idea to compute the cohomology of the spheres, it will be by induction. Because once that we know this, we will be able to compute the next in dimension, and so on. Okay, so we prove 1, and then I will leave you to think about that. And that's it for today. So I don't know if you have any questions or comments.
This proposition about having the same homotopy type is implies the same cohomology. Does it go the other way around?
Oh, okay. So, that is the question, Salvador?
Yes.
Okay, great. And of course here, this is as vector spaces. The answer is no. Okay. Let's see if what we have seen. Basically, we have seen only Euclidean spaces and the circle. No, for what we have seen so far, yeah, I mean, so far we have the example for which we know cohomology. Yeah, forget about equality, yes. For which spaces do we know cohomology so far? The circle and Euclidean space. That's all that we have, right? With those examples, we can still, there's no counterexample to your question. The answer is no. Okay, and so maybe by next week, when we get more examples, we can show an example of something that have the same cohomology, but they are not of the same homotopy type. Now, as I wrote it down, also is very weak because this is something that it is important to notice for any of you. Right now, I'm just focusing on the linear aspect of cohomology. But you can also ask, remember that we have a product, the wedge product. Then, because if you say, okay, the answer for this is no, maybe I will need a stronger assumption. And that stronger assumption can be, well, I don't want only that the vector spaces are isomorphic in each degree, but I want the whole cohomology, the algebraic structure of the cohomology to be equal, right? And that will be also something different. And the answer is still no, even with this stronger assumption. Okay. Yeah, so I have been only just dealing with this lighter aspect of it. But one can also be more curious about the entire algebra. Okay. Right. Any other questions?
Tomorrow's talk is at the same time.
Yes, yes. So tomorrow we will meet again at 10. Yes, and we will have Lauren's class.
Do you happen
Okay.
to know what it will be about?
He only mentioned application of differential forms. So he's going to be talking about differential forms, but I don't know if he will just stick with differential forms or go into I don't think he will move into cohomology, but maybe he will address differential forms that are close or exact. He will do applications of differential forms. Okay. And now, so remember, if we forget cohomology, just stick with differential forms. For what you have learned with differential forms and the exterior derivative, there is an exercise in the homework regarding that, and also in Daniel's talk. You just write down one sentence, one formula, but it involves many equations like Hamilton's equations. I think also Fabian wrote Hamilton's equation, but you can write down those in terms of differential forms in just one short equation. So that's why differential forms are very useful. It is a very good language to keep track of many types of information. So we will see what will Lauren talk about tomorrow. Okay? Great. Well, see you tomorrow then.